Hello. Hi, Vijay. Hello, Vijay. I'm unable to hear you.
Oh, okay. I was muted. Do you hear me now?
Yeah.
Okay. All right. Let me go ahead and share my screen, and then I guess we're just waiting around for some people to show.
Right.
Just hang on a sec.
So while we wait, right? I
Mhm.
just wanted to open that Notion link. I've added some notes. I've been listening to though I'm unable to attend all the sessions, right? I've
Mhm.
been listening to the recordings and I've been adding some notes. I realize people are not looking at the notes from the discussion. So I thought probably it helps to just quickly run through the notes for 5 to 10 minutes today and then continue.
Sure. Okay. Yeah, I think that's a great idea. Let me get the notes as well, so that way we can take a look at that here. So
Yeah.
notes are actually.
Hi, Akansha.
Hey,
Yeah, Kancha. Are you
hello.
doing a bloom filter talk today? Just out of
Oh
curiosity.
yeah, that's why I had sent those. Yes.
Okay, all right.
Can
We'll
we
do
start
that.
with that?
Yeah, we'll do
Yeah,
that in
yeah.
a few minutes.
Yeah. Just
Um,
give me 1 minute to
yeah, here are the notes, and let me just log in. Let's do that one more time. Okay, here we go.
Yeah, if you can just scroll down a bit, right? I had added notes for a couple of topics. So if you just go down. So all these were there, and yeah. So one is the LSM tree, one is regarding Bloom filters. Then
Okay.
if you go down,
B tree.
trees, compaction. Come
Range
down, and
query.
then something about clustered index and then non-clustered index. So let's wait for a few minutes before we get started. So I just tried to, add some diagrams so that it will remain in our minds when we are kind of going through.
Yeah, good
So
job here. Yeah.
let's just wait.
Okay. I think we can wait a few more minutes, but I don't want to wait too long because I know that
Oops.
some people are out sick today. And then Karthik usually shows up late anyway, so not to knock on
Okay.
Karthik, so he'll join anyway later.
Mhm.
So let's go ahead and just kind of start. I think that would be the best thing for now.
Yeah, sure.
So do we want to start with this review and then go to the Bloom filter and then go to the top of the chapter, finish the chapter? Is that a good strategy?
Yeah, maybe Elasticsearch, I think the first two diagrams, I believe Amulya had added.
Mhm.
Maybe she can give a better talk of that.
Okay,
So
let's jump down to LSM.
yeah, I had added this engram, but that was some time back, so I don't kind of recollect. Maybe we can get started from here.
Mhm.
So
So
yeah,
what is it
it's just
off the top of your head? Like, right, pretend that this is like an interview question, but not like a serious one. What is an LSM tree? What does that even stand for?
yeah, that's log structured merge tree. So
Right.
if you look at the log structured merge tree, right, you basically have a number of components. That's how I look at it. So you can think of it like we are having certain in-memory components and certain on-disk components. So in memory, right, we typically have a mem table, and on the disk we have the SS table. So what happens is like and we also have this Bloom filter so that we can do some easier, faster read requests. Then since we have this mem table on the memory, right? We would want to have some kind of a mechanism to kind of build up the mem table in case some crashes happen. So we have the write ahead log for the same thing. So basically what happens is like whenever a write request comes, right, the first thing is to push the request onto the write ahead log so that we don't miss it in case there is some process crash or something like that. The second is to go ahead and add it into the mem table. The mem table could be a balanced search tree where it could be some red black tree or some any kind of a balancing tree. Then we also added to the Bloom filter. So whenever a read comes, right, the first thing is to query the Bloom filter. If it is not, what do you say? If it says, yes, it is definitely present, right? Then we can go ahead and look at the mem table, search for it. If it is not present in that, then of course we can build a index on top of the SS table as well. So, and then the once the index is queried, and if it is not present, then we can go ahead and look into the SS table. And these SS tables, in the background, we have this compaction process which takes place to go ahead and reduce the SS tables or compact it so that not much of disk space is utilized. So
Hey,
that's
Sadhna, can you tell more about the secondary index on SS table?
Where are you seeing?
There is, sorry, in-memory index on SS table.
Yeah, it's just an index kind in order to search the SS table. So I was seeing a couple of different ways by which they build this whole LSM tree. So one particular way is like, I mean, instead of going ahead and searching in the SS table, right? So the way to sort it, you have to do a disk read, right? Instead of that, they also maintain some in-memory indexes just for faster querying purposes.
So there are two same names being stored in the SS table, like same key value. Both
Correct. I mean, that will happen when the compaction has not yet processed, right? So you can have multiple SS tables with what do you say, the same key.
Yeah, so there will be an index on both the keys, right?
Yes.
Okay.
So that is one part, and
that was a good explanation, by the way. That was really good. Did you draw this, or did it come from this article? I was curious.
I've added all the references, diagram reference.
Okay, so was it the diagram in here?
Yeah.
Okay. All right, cool. I was just gonna say it looks very good.
Yeah, I mean, I kind of I can relate. I can remember things only when I have diagrams. So all the notes below has one or the other diagram. Otherwise, I will tend to forget things.
Yeah, no, this is really, really great. This helps a lot because there's the wall, there's the mem table, there's the Bloom filter. This is the write side. This is the read side. Here's your index. Index lets you know where the location of the file is, or the content is, I suppose. And then here's the main table. Here's a memory table to just kind of fast get whatever you need. And then the compaction process that we talked about. And then you're right, log structured merge tree. Yeah, right. Like, so when I think of LSM, it's appending only, right? Like it's an append algorithm. Whereas you compare that to the B tree, which is kind of more like an overwriting algorithm that it's like has a whole bunch of references to values that you can like just jump to, correct? Like down into the tree. So yeah, LSM versus B trees. You use LSM trees for mainly writes, and then B trees for reads. And then you want to keep the B tree kind of as small as you can. So that reads are
Its
fast.
height tends to be only say around 3 to 4, even for 250 terabyte of data.
Mhm.
So so that way it is good. And yeah, if you see, Bloom filters, probably I'll let Akanksha talk, but yeah, there is a good explanation here with the diagrams. People should be able to understand it. And so if you go down, right?
Mhm. You want me
Okay,
to jump to a
I'll
particular
just,
section?
yeah, I mean, maybe Bloom filters, I'll let Akanksha talk. So,
Let's do bloom filter now. Okay, so all right, Akansha, you're up.
Yes, I'll share my screen. So if you can stop that.
Oh yeah, of course. Let me just give you hosting privileges too. Here you go.
I think she's not there. Has she dropped off?
Oh, okay. I'll message her so we can get her back. She might have made a mistake.
Yeah, instead of sharing, she might have just clicked on leave. Yeah, maybe while she's back, right, we can discuss on we can get started with the other one, and while she comes back, she can take over the Bloom filter part.
Looks like she
But I
just
think
got
she's
back.
joined.
Okay.
Yeah.
I will share my screen. Host disabled participant screen sharing.
Try again. I'm giving it to you again. I think you got dropped.
Okay. So okay, so Bloom filters
Yes,
are,
example, I put it in the notes as well.
I'm sorry.
This is so no, that even in that Notion notes, I've added the example from the Geeks for Geeks article only.
Oh,
So it's so
nice.
self-explanatory.
Yeah, self-explanatory. So Bloom filters are it's a data structure, but the special part about this data structure is that it is a probabilistic data structure. It is also space efficient. Now we'll discuss why it is probabilistic further down. There is a Bloom filter. It uses a bit array, and initially the bit array is initialized to 0. It's all set to 0. So it's something like this, as you see. The concept behind the Bloom filter is it uses hash functions. So you see here there are 3 like hash functions being used. So it's not necessary you use 3 hash functions. You can use more than 3 as well. It depends upon how efficient Bloom filtering you want to establish. And I'll tell you, if you increase the number of hash functions, how it impacts your Bloom filter. It will come down to it. So let's imagine you have a bit array and you have three hash functions. Now you want to store geeks, the word geeks in it. Now this is a 10-bit, right, array. So you pass pass the string and you modulo 10 because this is a 10-bit array, and you get these locations. Now these 3 hash functions are all 3 different. So at position 1, 4, and 7, what you will do is, initially it was all 0. Now you have set it to 1 because that is what your hash function gave you, these 3 positions. Now I want to store the string nerd. So after passing the string nerd from these 3 hash functions, I get 3, 5, and 4, and I store them at these locations. Now, if you want to check geeks is present in the filter or not, you need to go through the same process. But what you will do is we calculate the respective hashes using H1, H2, H3, and you will check at these indices that if they are all set to 1. If they are all set to 1 in the bit array, that means if all the bits are set, we can say that geeks is probably present. Now, important point is I'm saying it is probably present. If any of these indices is set to 0, then geeks is definitely not present. Okay, so I can explain you this with an example. Say for this example, for this thing cat, we did not store the word cat, we stored geeks and nerd, and we are getting position 1, 3, and 7. So we see at position 1 it is set to 1, at position 1 it is set to 1, and at position 3 it is set to 1, at position 7 it is set to 1. But did we really store cat? We did not. So it can give you a false positive here. So that's why it is said that if any of the bit is set to 0, then we are sure that this word is not present. But you can say that, okay, if you're getting all ones, then it is probably present. And that is why it is probabilistic, and that is why there is an uncertainty. So that is what the Bloom filter concept is all about. One thing to note about in Bloom filter is you cannot delete from a Bloom filter. You can only add to it, insert, and you can do the operations allowed are insert and lookup. Okay, and they are pretty space efficient, and the larger the Bloom so if you're when they are implemented in real life, you don't just use 3 hash functions. Here we gave this example, but in real life they are maybe 11 or 15 hash functions. So the false positives that you are getting, the chances of that will reduce as you improve on your hashing strategies. So that is what I had this not this one. So this is an example. So it was an interactive one, so I just wanted to show. So if you add a key here, you see how this key is mapped at 3 different positions, right? And so this is how and if you add so the key gets mapped to different positions, and in your bit vector, and the k different hashes that you are using, depending upon the number of hashes you are using, your Bloom filter efficiency will also improve. Example of what Sadhana just spoke, we use Bloom filter in SS table, and so that's one implementation that I started in the book. But there are other implementations, what Amulya was speaking, the way Facebook uses it in lookup of the usernames. So that's another use case. But yeah, I think that's all I wanted to share with you all.
Great job. That was an excellent explanation. And you made it a very, it could be kind of difficult topic, right? Like you made it very, very simple to understand. So that was a good job. Excellent. Anybody else have anything to add?
Yeah, maybe we can just continue with that notes. Just one more topic I think I've added.
Okay.
So I've just added another diagram which will help us to remember things. So if you look at that on top, right, that Bloom filter is, I've already added the notes for it. So that it's like geeks for geeks, the same explanation which Akanksha had spoken.
Mm-hmm.
So we can use that as a reference. So come down.
Okay.
The other one which I wanted to kind of, I haven't gone through very deep into compaction differences in the 2 types of compaction, okay? But I thought a diagram will kind of help us to remember what is the difference between the leveling compaction and the size tiered compaction. So size tiered compaction, right? What happens is like if you open that below one, second one is your size tiered compaction. So in your size tiered compaction, what happens is like, as and when the SS tables grow to the same size. So the first box which you see, right, which contains 4 SS tables. So they're all of the same size. So it could be some KBs. So XKB, 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 XKB. So when all of them say default is 4. So when we have defaulted the number to 4, right? So when we have 4 different SS tables of the same size, then they go ahead and merge it to become one more bigger SS table, right? So now we wait for that particular sized SS table to grow for the same X number of times. So that is 4 times. So default is 4. So now once we have got the next 4, right, it goes ahead and merges into another big one. So that's why in your size tiered compaction strategy, what happens is like the size, the disk space consumed is very high. Just imagine that huge box, the last box, whatever you have, right? As and when it now you're waiting for that such a huge box 4 times to fill, and after you have merged it, that is going to be a very a bigger one now. So it is like, say, for example, if the disk space is like 50% already consumed. So now if you have to, or rather 51% if it is consumed, right? For after merging, you will not be able to put your the other merged part. So only after you have created that merged one, you can go ahead and delete the older ones, right? So that is where leveling compaction probably level compaction comes into picture, where it does not use so much of disk space. So level compaction, I'm not, just go up a bit. Level compaction, I haven't understood it completely, but if you just open it, right? So all that I understand is it's like it is having multiple levels. So the first one, that key value, whatever you write, right? On the right hand side, whatever you have is your log. That is probably your write ahead log. And on your left hand side, you have that mem table. And probably, I mean, they have something called as an immutable mem table as well, before they flush it onto the SS tables. So now always it gets flushed to the level 0, which is then, I don't know, I haven't gone through this in deep, but after that level 0, right, it gets pushed to level 1, then level 1 to level 2, level 2 to it goes on to level K. But if you see, the size is like incrementally growing, and you're not actually, you don't need so much of size, I mean disk space, as compared to your size tiered compaction logic. And if you just go back, right, there is one interesting graph which they have shown, which I think that is more important for us. So when exactly, in which use cases we can use kind. So in case of your tiered compaction, right, and your level compaction, in your level compaction, it kind of helps in faster read, and it is slower in write. Whereas in your tiered compaction, it so happens that faster write and slower read. So how I see it is like, in case of size tiered compaction, right? You don't have to see where to insert it, kind. You're just dumping it onto the SS table. So I'm not very sure, but this is an interesting graph. Probably we'll have to explore a bit more to kind of understand this, how they have come to this conclusion. But for our use cases purposes, right, in case somebody wants to choose when to use tiered compaction and when to use level compaction, right, probably this will help us to decide.
Yeah, this is again, I think this is a good explanation. These are some simple graphs that kind of help people kind of remember, the ideas behind compaction, and then how,
Right.
These SS tables kind of grow in size as they get merged, and how the disk size also kind of becomes bigger with the SS table. I don't know if this represents leveled. Maybe this graph here is a leveled compaction.
Yeah, the first one is your level compaction only. But I have, I did not get time to kind of dig deeper into that level
Finding
compaction.
a tiered one. Yeah, because no, I was just saying, like, maybe we should have like a picture for a tiered compaction as well, so you can see them side by side.
Size tiered is here.
Okay, so size tiered compaction, then this one's leveled. Okay, so at the very basics, right? Like when you're doing compaction, like you're just kind of saying like you want to remove this duplicate, like, or you want to get like the latest key and value, right? Is that kind of what that's what I remember, at least from the compaction process. So is that what's kind of being talked about here in these diagrams as they merge?
Yeah, I think as and when the levels grow, right? As and when we start inserting, you will require more size. So looks like they will allocate one more size and they'll push it to the next level. Whatever is there in your, if you see, there are these arrows which says level 0, whatever, whatever you write initially is always pushed onto your level 0. So
Okay.
next, after you have, after a particular size, it hits that limit, right? It is then pushed to level 1.
Makes
So, but
sense. Okay.
how exactly that merging happens is something which I will have to double click and then understand a bit more. But I thought it is useful to have this in our mind. At least size tiered looks simpler to kind of understand. But leveled is something which we have to understand a bit more. But yeah.
Okay. All right. Yeah. Great job. Great job with the notes as well. And just getting all
And
this
come down,
together.
come down.
Okay.
Yeah, the last part of it, what I had written was, yeah, of course, we have to still write about that range query part and the right amplification range query, which is better and with respect to right amplification, all of this thing. But for now, right, I've written regarding the heap files, clustered index, and then the covering index. That was the last thing which you guys discussed last time, I believe.
Right.
So heap file is more to do with it's just an unstructured data which you keep adding it, right? And with respect to your clustered index and then non-clustered index, right? In the case of your clustered index, in your B tree itself, you have your data also stored in your leaf node. Whereas when you say it is a non-clustered index, right? You have the leaf node pointer. In the non-clustered index part, right? You typically have in the leaf node, you just have a pointer and you don't have it. You don't have the data stored. You have a pointer to that data. So typically how the systems are designed is like you have the primary index, which will be stored in the clustered which will be stored as a clustered index so that it is easier for query. However, in a secondary index, right, you can have multiple indexes. Secondary index is going to point to your primary index and primary index is going to point to your data. So clustered primary indexes are typically configured as your clustered index and your secondary indexes are configured as your non-clustered index. And sometimes, right, a non-clustered index, what happens is like you have to, it's like it is happening, there is one hop. So that is like causing more latency kind. You have to do one more hop to reach the actual data. And in your clustered index, you have to store all the data in that table, right? So a key map to a particular column value. So all the data, so that is going to increase the size. So a kind of midpoint between your clustered index and your non-clustered index is something called as a covering index. So in the covering index, right, you don't store all the columns like your clustered index, nor is it just a pointer. So you have some of the tables columns which will be stored along with the index. So probably for the remaining set of columns, they will have a pointer. So it's a mid between your clustered index and your non-clustered index.
Hey, Sadhna, so this
Mhm.
leaf data is stored on the disk, leaf in the clustered index, right?
Yes.
No data. This is stored on the disk, and these for the secondary index, these pointers are also on the disk. They are, because this data is on the disk. So even the non-clustered index is present on the disk. It's being
Correct.
created on the disk, and the pointers are pointing within the disk, right?
Correct. But what will happen is like your non-clustered index can be more sparse. You don't need to have your primary index. What happens in your typically when you design the system, right? Your primary index will be more dense. That means primary index will have index to every other entry. Whereas in your secondary index, right? Say for example, if I don't have a diagram to rightly explain, but if you can just imagine, right? Say for example, take the example of your SS table itself. In your primary, say you create a primary index for the first SS table. So say records 1 to 10 is present as a primary index, and it is pointing to your SS table. Similarly, 10 to 20 in one is present. When you create your secondary index, right? How do I explain? All that I'm trying to say is 1 to 10 will be present in one particular file. 10 to 20 will be present in one more file. All 1, 2, 3 sequentially, everything will be present. 10 to 20 will again be sequentially present. Now you can have an index, secondary index created only to 1 and 11. 1 will be pointing to your first primary index, the first one, and 11 will be pointing to your second primary index. So did I make sense? So it is a sparse index. So when you query, right, it is like it is easier for range query. So you always know 1 to 10. You can, when you hit the secondary index, right, from 1 to 10, you can go to the first block. Okay, I'll try to find a diagram. I'm not sure if I'm making.
No, Amulya, sorry, Sadhana, what I read was there are double pointers, and like on these leaf nodes, it's like imagine like a W linked list. So double pointers, and they can travel. So imagine you're writing your query not from X is greater than, say I write my query, X is greater than 5 and X is less, and X is less than 12, right? But you than
Hello.
5. So the way you are structuring your query, I mean, so I think there are doubly pointers. That's what I read.
Can you show a diagram? Maybe it will be
I
helpful.
don't have the diagram, but I will put it on the WhatsApp chat group.
Yeah, we will. I'll go through that. I just tried to get some concepts. Yeah, I will go through the other one as well. You're telling how exactly. Yeah, I did see one more where you have in the B plus tree, right? In your leaf nodes, all are connected through your block pointers. Is that what you're referring to?
Yes.
Yeah, I will go through that and I'll try to add some more notes, Akanksha. Maybe you can give me reference to whatever you're pointing to, but this is a general idea.
Yeah. This looks good. Yeah, I have this one
Yeah.
here. Yeah.
You have the basic idea here too, right? You have the diagram for the non-clustered index, and then you have the clustered index. So, I think this itself kind of speaks a lot, right? This one shows you that you have pointers, whereas this one has data. And then I don't know about the implementation, which you're also kind of saying it could be a doubly linked list, or it could be like the B tree as an example. So, but you're right about the ranges, right? It's meant to find like a range, like, 0 through 9, or 10 through 11, 20 or something like that. So this kind of these kind of data structures, clustered indexers, are supposed to help with finding ranges, like when you make like a SQL query. So this is pretty good though. It's a good first start. All right. Does anybody want to add anything else like to what we discussed, or shall we move on to the book? Okay, well, this is good. I think like we have the basics here. LSM trees, the bloom filter, which was really good. This diagram is really good too.
I'll try to add diagram for B tree as well. I did not add it. I will add that. But I have a question though. I always, I'm kind of reading something, a few things differently. Does B tree have all the data stored in your leaf nodes, or does only B plus tree have it stored in your leaf nodes? I thought B plus tree alone has and not the B tree.
So one thing that
is where all the data is scattered again.
Right. So one thing, I mean, like that I can point to from the book is just they didn't really go into detail about B plus trees. They just kind of talked about B trees in general, right? And it kind of looks like this diagram that you have so far, where, like I think this partially explains it. You've got a tree, root node. It contains references. Here they say pointers. And then the pointers point to a value. This all lives in like a heap area, like an unsorted area. So it's called a heap file. When they add a new key, then they have to split, the row, right? And then, so with a B tree, you always kind of have like extra space that could be unused each time you make a split. But the cool thing, I guess, about it is that like it helps support like, okay, so you're looking for this range. Well, here's this number that you're looking for. It's probably in this side, or it's probably in this side. So you get like kind of like this log n kind of, fashion of like retrieving data, right? So that's why they say it's good for reading as opposed to writing. Writing is like, this time consumptive thing that happens when every time you add a key. But if it's pretty balanced, then like you can say, all right, you're looking for a range 0 to 10. Here it is. Like, this is where this row is. And then the iterator can just kind of go through and go, oh, here's what you're looking for. And here's all the stuff and return it back, right? It's kind of like what I got, at least from a B tree. And here they kind of say kind of the same thing.
Vijay, can you just open that Geeks for Geeks link, which I just posted?
Sure.
Put it on the chat.
Sure. Okay,
If you
cool.
just come down, right? They have the differences.
So you want me to start here?
No, there is a table which shows the difference.
Okay,
Here,
right here. Okay.
here. So
Does
that's what
anybody
they
know
are
how to
telling.
make this instead of dark mode, light mode? It's kind of,
I'm not sure.
yeah. All right, well, we'll come back to this. I'm just like a UI person, so I hate like jarring colors. So all right.
Okay. So if you look at the second point, right? Your B tree is not, all the data is not present on the leaf. It will be present everywhere. Whereas in your B plus tree, right, it will be stored at your leaf nodes. And in your B plus tree, you will have all the data which will be, what do you say? It will be connected. All your leaf nodes will be connected. I'm sorry. I mean, I'll just get some water. Maybe you guys can just go through that.
Okay, yeah. No worries. All right, so I'll kind of read this here. So a B tree, all the internal leaf nodes have data pointers, whereas leaf nodes have data pointers. So like the end, I suppose, have data pointers. All keys are not available on the leaf. Search often takes more time. All keys are on the leaf nodes, hence search is faster and accurate. No duplicate keys is maintained, but here you can have a duplicate key. Insertion takes more time and it's not predictable. Insertion is easier and results are always the same. Excuse me.
Why is insertion faster here in B plus tree?
Let's take a look here. So, so this is like your basic B tree. And then here's a B plus tree. And so here you have a pointer, and then it has another pointer, and then this is a data pointer. So let's read here. A B plus tree eliminates the drawback B tree used for indexing by storing data pointers only at the leaf nodes of the tree. So at the leaf nodes of the tree here, right? So these are the leaves. So the data pointers, thus the structure of the leaf nodes of the B plus tree are different from the structure of internal nodes for B tree. It may be noted here that since data pointers are present only at the leaf nodes must necessarily store all the keys along with their corresponding data pointers to the disk block. So where does it show the keys? I guess, is a key this thing here, or is that a value? In order to access them. So moreover, the leaf nodes are linked to providing ordered access to the records. Okay, so that's why. So here's 2, then 3, then 4, then 5, then 9, 10. So ordered access. The leaf nodes therefore form the first level of the index, with the internal nodes forming the other levels of the multi-level index. Some key values.
So this is exactly what I was trying to explain. So if you see that leaf nodes, right, that is your primary index, which kind of has pointers to every other data. Whereas your secondary index, which is on top, your 3 and 5 is a sparse index. So it may not have, it kind of points only to one particular record.
I see.
So this is exactly, since I didn't have a diagram, I was not explaining.
How is 3 is not pointing to a record? It's a leaf node that is
it's not pointing. So it's just pointing to another index. So how they configure is like your leaf nodes are configured as your primary index.
Yes.
On
Alright.
top of it is your secondary index. So secondary index is your 3 and 5. So 3 is pointing to your primary index, which then leads you to the data pointer.
Okay, so secondary indexes are then using B plus trees, right? What like the non-clustered index that we create.
I mean, that is right, at least in this case, but I'm not sure if you can do the same thing in B tree. So that's where I was kind of
Okay,
trying to
why is
understand.
insertion faster in B plus tree?
I'm not very sure. I'll have to understand that a bit more. Searching, probably they'll do a sequential scan on the leaf node. So that is probably the reason why it is probably faster. But why is insertion faster is something I'm not sure.
Let's see. Sometimes I like to go to multiple sources beyond like the typical ones. So let's take a look at like Stack Overflow as well and some of these places. So here's a B tree, right? And it says the image below shows an example of a B tree. The maximum number of children in this tree is 3. And we can conclude this tree is an order of 3. So you can have max children 3 leaves. And this tree is an order of 3, so height 3. All the leaves are on the same level and the root and internal nodes have a minimum of 2 children, fulfilling the conditions of the B tree. And let's see. And jump down just a little bit to see if he talks about B plus trees. The B plus tree. So the most well-known version of the B tree is the B plus tree. So maybe this is like an advanced B tree, right? Like once you have the concepts of the regular B tree down, then like you should be able to understand like a B plus tree. And here's your doubly linked list. All the leaf nodes are linked together in a doubly linked list. So that could be part of the reason why like retrieval or deletion is easier, because like if you have a doubly linked list, then you can just kind of jump directly to like a point, you know, at a node and then remove.
Yeah, because of doubly linked list, it might be faster. Insertion, deletion, everything will be faster.
Whereas this takes way more time because you have to like, you know, cut, then like separate the leaves. And then you have to balance it out. Yeah.
Balance it out, yes.
Okay, cool. I'm gonna put this link. Well, I'll put it here too. In this.
As well, you still have to balance it, right? You cannot just go ahead and add the data onto your leaf nodes. You still need the tree to be balanced.
True, but I think.
B plus tree?
Go ahead.
You're talking about the B plus tree needs to be balanced? Both
of them has to be balanced. So,
but is there is there a condition in the B plus tree that number of children have to be a minimum number of children has to be there? Like in B tree, there was a constraint.
Meaning a number of.
So in B tree, if you go, it says that there are some conditions you need to follow, right? It is an N array B tree or something. So.
Yeah, back at the top.
Let's do one thing. Let's go through the differences correctly, and then we'll discuss the next session probably, rather than trying to explore now. So maybe we can go through something which probably I haven't read the remaining part of the chapter. So maybe Vijay, if you've read it, we can just go through that.
Yeah. Okay. So the big high level thing here is not to get like caught up in like what is a B tree and what is a B plus tree and all that stuff. I think more, if anything, it's just that this is a, you know, data structure that powers, you know, sort of data retrieval. And so he doesn't even really go into like detail about what a B plus tree is. I think he just keeps it simple with a B tree itself. And, you know, again, it's just kind of like you refer to these as pages, right? And, you know, like when you're retrieving a page, you can say, okay, well, like this range is probably in this area. And then you have that Bloom filter also, right? That kind of helps together, like give you like a probability, like, I can't even say the word here, but like the probability of like the data that you're looking for is probably in this B tree. So it's just about data optimization, making it faster to get information, and then making it faster to also manage the information that grows, right, by the balancing that goes on in the background. And then again, B trees are meant more for reads, not for writes. So if we jump past all this, right, I think we got up to the point where we were looking at multi-column indexes last time. And multi-column indexes kind of build on like all of the stuff that we've been talking about so far. So with a B tree, like you're not able to get an answer for a query like this, right? Says if you write the following in SQL, select all from restaurants where the latitude and the latitude is less than 51 and greater than, or I'm saying latitude is greater than 51 and then less than 51.507. And then longitude is greater than 0.1162 and less than 0.1, right? So this range, it says that an LSM tree or a B tree cannot answer this query efficiently. In order for you to do a better query, you need a multi-column index. And so this is basically where you combine several fields into one key by appending one column to another. And, so it's like, he says here, an example of this would be like an old paper book, which provides an index from last name and first name to phone number. So you can find all the people with a particular last name or all the people with a particular last name first combination. However, you can't find anybody if you're trying to search by first name. So this is where the need for like, simplifying like what a multi-dimensional index looks like. So here he says, when a user is looking for restaurants on a map, the website needs to search for all the restaurants within a rectangular map that the user is currently viewing. So let's go on to the next page. So one option is to translate a two-dimensional location into a single number, right? So take the longitude and latitude and create something like a space filling curve, and then use a regular B tree index. So you use the B tree index and you use it to point to a space filling curve that represents a two-dimensional location. Specialized spatial indexes such as R trees are used. So, there are things that are more complicated than the B tree. There's an R tree. So there's a software called PostGIS, and it implements geospatial indexes at R trees using PostgreSQL's generalized search tree indexing facility. So this would probably be something to go and take a look at too. But I would say at this point, like, don't spend too much time on this and getting lost in this detail. I think keep it more high level, and how like we manage data and how do we make it easy to like work with growing huge data at scale, right? That's kind of like the big picture. And what database would you choose if you were to pick up an application today, or you start writing an application? Would you use one that's LSM backed, or would you use one that is B tree backed, or something more specialized? And obviously, if you pick something more specialized, you definitely need to kind of go and research what that backing is. So maybe like the R tree in that respect. Here's another one where it's three-dimensional index on dimensions like red, green, blue. So if you're searching for an e-commerce site for finding red, green, and blue clothes, or if you're trying to do a two-dimensional index for date and temperature, then you want a database essentially that can support these multiple indexes. So, and then he also just kind of mentions another software called Hyperdext. Then basically the next part of this chapter is called, talks about full text search and fuzzy indexes. So interestingly enough, like I think like somebody asked this to me like on an interview call one time, and like I didn't really know, but I was reading through this section here and I was just like, oh wow, okay, like this probably kind of explains it pretty well. Like how would you search for something? And it support kind of like mistakes. So here he says fuzzy querying requires different techniques. So for example, full text search engines allow a search for one word to be expanded to include synonyms of the word, to ignore grammatical variations of words, and to search for occurrences of words near the same document, and support various features that depend on the linguistic analysis of the text. So to cope for typos in documents or queries, Lucene is able to search for words with a certain edit distance. And so that could be like, you know, one letter off from the original word. He says that the structure requires a small in-memory index that tells the queries which offset in the sorted file they need to look for the key. So once they find that key, then there's a state machine that I kind of, this is like the aha moment for me, right? Like when he says finite state automaton, to me, that just kind of means like this is a state machine and there's always like one state that the machine is in, right? And so if you use like this Levenstein automaton, right? Then basically it's kind of, if you, and I wish there was a diagram for it, but like maybe I can pull it up on Google actually. Like a tree or a try, right? I guess like that's probably how you say it to like for other people to understand what you're saying, is kind of like, you know, this long list of letters, right? You can imagine like I have a try for like Amy, and then I have another try for Akansha, right? And then I have another try for Karthik, right? So if I go down my tree, I know, okay, this is like, you know, the here are all the possibilities for A, here are all the possibilities for the first name, B, and then so on. And so this finite state automaton just kind of keeps track of like the key that you're looking for and the value. So this is kind of like an interesting thing. And then it supports efficient search for words within a given edit. So if you make a mistake, it can still give you back like a word that kind of looks similar to like what you're searching for. Does anybody want me to stop there and just kind of look up a diagram? Okay, I think I can also do that afterwards. Like when I go and research, I can like add a diagram into the notes. I think that would be a good idea, because this is, again, like an interesting topic, and I think it might come up in an interview. So other fuzzy search techniques go in the direction of document classification and machine learning. So see an information retrieval textbook for more detail, right? Like I think this is all like the most popular stuff right now. Like if you wanted to get a job in machine learning or whatever, right? Then maybe like contributing to fuzzy search techniques. So then here, this is another thing that I was talking about last time, like how this chapter is kind of like moving us from like storing stuff in the data to in memory, because memory is just faster and cheaper. So he says here, data structures so far in this chapter have been answers to the limitation of disks. Compared to main memory, disks are awkward to deal with. Both magnetic disks and SSDs, data on disk needs to be laid out carefully if you want good performance on reads and writes. But we tolerate this awkwardness because disks have two significant advantages. They're durable, meaning you can like drop the disk, maybe. Their contents are not lost if the power is turned off. That's probably what he really means. And then they have a lower cost per gigabyte than RAM. But RAM is becoming cheaper, and the cost per gigabyte argument is kind of going away. Data sets are also not that big, right? Like the data that most people use, like even small businesses, right? If you were to work with a small business, probably a lot of their data, like they're just managing it in something like Excel, right? Like a whole bunch of Excel sheets with light SQL. So maybe like a simple database for them, is probably appropriate. And it could even be like the case that some of it could be just moved to in-memory, right? So he says that many data sets are not that big, so it's feasible to keep them in memory, potentially distributed across several machines. And then this has led to development of in-memory databases. One in-memory key value store is called Memcached. I hear people sometimes say meme cached. I don't know if they're trying to say memes, but maybe it's to be funny. So Memcached or meme cache, it says that this is acceptable if data can be lost, if the machine is restarted, but other memory databases aim for durability, which can be achieved with special hardware like a battery powered RAM, writing a change of logs to a disk periodically called snapshots, and then replicating the in-memory state in machines. So, like I think this is partially like that write-ahead strategy that we saw before, write-ahead log, plus like an in-memory database, and then there is no disk use. And that could be tolerable. When an in-memory database is restarted, it needs to reload its state, either from the disk or over a network via a replica. And kind of this makes a little bit of sense, right? Like in some web applications, you have like most of your data like sitting inside local storage, right? Or some kind of like simple cookie or something like that. And then you just load it into your application memory, and then you're good to go to the races, right? You don't really need a whole bunch of other stuff. And then that app can just kind of be like easily like, worked with like for the client. So that might be like a good enough solution. And I was talking to a friend actually who was saying that like there's this company that he's been working with that is like trying to like pitch more to people that you don't really need huge databases. You can just kind of use like a good caching solution, and that should be good enough for like your most applications that you're working with. It should be faster. So I can get information on that later. So before I go on though, it is 8:31. Does anybody want me to like stop here or say anything, or shall we continue with this section into next time? And if you're saying anything, just make sure you're not muted.
Yeah, we can continue next time, I think.
Okay. All right. Sadhana, I see you opened up your mic.
I'm okay to continue. It's Friday evening for me. If you guys have work now, then probably we can stop and then take it the next week.
Do you want a few more minutes?
I'm okay if others are okay.
No one has a hard stop, I guess. Okay, if you have a hard stop, feel free to drop. Don't even wait for me to say anything. That's not a big deal. Okay. All right, so I'll just go on for a few more minutes and then I'll stop too, because I actually have to get ready for another meeting. So yeah, basically like caching could be a good strategy for, an application you're working with. Especially if you can find like a workaround for like, reading fast from a disk or like from a text file or something. Volt, DB, MEMS, SQL, Oracle ×10 are in-memory databases with a relational model. And the vendors claim that they can offer big performance improvements by removing all the overheads with managing on disk data structures. Then you also have RAM Cloud, in open source in-memory key value store with durability. Then you have Redis and Couchbase, which provide weak durability. And here that Redis and Couchbase are sort of like the most popular for, in-memory databases. So this could be, like another reason why like this is probably so popular in web development. The performance of in-memory database is not due to the fact that I don't need to read from a disk. Even disk-based storage engine may never need to read from disk if you have enough memory. And let's see here. So I'm going to go to the next section here, because like I think we kind of understand the advantages of using in memory. But here he kind of says like another interesting area for in-memory databases is providing data models that are difficult to implement with disk-based indexes. So Redis offers database like interface to various data structures like priority queues, right? And sets. So it's easier to make like simpler data structures with in-memory than it is with disk, because all of the data is in memory. The implementation is really simple. So then here they talk about recent research indicates that an in-memory database architecture could be extended to support data sets in larger than available memory without bringing back the overheads of a disk-centric architecture. This is called an anti-caching approach, and it works by evicting the least recently used data from memory and puts that in the disk when there's not enough memory, loading it back into memory when it is accessed from the future again. This is similar to what operating systems do with a virtual swap and the memory, or virtual memory and the swap. The database can manage memory more efficiently than OSs. This approach requires indexes to fit in memory though. So bitcache example at the beginning. And then further changes to storage design will be needed if non-volatile memory technologies become more widely adopted. So this is a new area of research, but it might be worth keeping an eye on. So maybe Karthik at some point, if you want to like look into this, that might be kind of, because I know this is like the stuff you are interested in as well. So I think we're at transaction processing or analytics. I think we can stop here, but I will say that we're pretty much almost there, because like the next few pages are just kind of about like a few things like analytics. Like he takes a turn from, so far what we've been doing is like we've been working with data that is mainly like read and write. But like after that, like you get into the section about like, so he calls the read and write stuff OLTP, but then there's on the other hand, like something called OLAP, and OLAP systems basically pull all of this OLTP data, right? Like as you're writing and reading from these different data sets. They're business people who pull all of this data together at a central data warehouse, or maybe like a data lake. I don't know if this whole thing is called a data lake. That's probably what it, but a data warehouse is where they can make business queries and transform, all of this stuff into understandable information. And so for business people, like most of that can be done with a conventional SQL database. So it's pretty interesting. That's kind of like the next part, and I think we can get through that in the next session. So yeah, as always, thanks for showing up. And then I will say like one more thing too, like I am seriously considering like doing this study group. I'm just like putting this out there, just if you want to see it. And it'd be kind of like the same as the one that we have right now, where it's, so I know that like I put a lot more hours of study here, but this is mainly on your own time. But it would be kind of like the same, right? We meet for an hour in the morning like we do right now, but we would just extend that with having like one particular day where we just practice only. And then another day where it's simpler, it's like just an hour of like discussion. And this is up for discussion as well. So if you want to review through the study group, just let me know. But what we tackle is all of this stuff.
interested. By the way, did you all find an accountability partners for yourself? I need one to keep myself committed to attend these sessions. Somehow or the other, I'm not able to kind of attend. So, but I do definitely try to catch up to listen to all the videos and then do my bit of contribution by adding some notes. But yeah, maybe I just want some, maybe half an hour or 1 hour per day, right? I want to really spend some time. So, did you all sign up for that accountability partner thing? Did Karthik or you?
I have not,
Karthik
but
is silent today.
I
Is
can.
he there?
Yeah, he's there, but I think he's been muted the entire time. So he might have fallen asleep. We can ask him though after the fact.
Oh no, just that the kids were a little too noisy today. Yeah, it's a little bit too much for me, that accountability thing and stuff like that. Just concentrating on different things. So most likely data structures and stuff, and I still
Yeah,
have to catch up.
accountability only for DSA and system design. I'm not committing for anything else.
Yeah, I mean, we can keep us honest. I don't need a system. That's what I'm trying to say. I don't really need a emailing system which is gonna say, do this, that. You know what I mean? I'm okay. I think I can keep myself honest. I try my best to. So yeah, everyone is different. So
I think
Yeah, I mean,
I think what he's trying to say is that, the accountability program that I think you're referring to is just probably going to email you every morning and say, hey, are you being accountable? Right? Whereas you know that you want to be accountable already. And so having a study group is going to help you do that, right? Otherwise, I can just hide this, right? And then I can just tell you guys, oh yeah, go study all this on your own, right? But I don't know if you're actually going to do it. And so, next time we might be talking about more complicated, for me, the reason I feel confident at talking about a B tree or a B plus tree is because I've spent significant amount of hours outside of just reading this book, to watching other things like these lectures, sitting there and reading another book on, data structures and algorithms, and, just making copious notes back up here, and then my whole plan too is to start lead coding as well. So, because you can't really say that this stuff unless you actually practice it. So that's what this is all about, just kind of the accountability is in the study group if you want to do this together. Otherwise, we don't have to. If some people kind of already know it, then I'll just kind of focus on it. But this is, for me, it's helped a lot in understanding this other book as well. So
no, I am definitely interested in, I just want to kind of, somehow the timings are not suiting for me. So, but yeah, I do, as I told you, right, I just go ahead and ensure I listen to it. So that's one thing I've been doing. I try to do my reading as well. Just that we'll have to come up with something, some more, a better time to kind of suit all of us.
Sure.
I think maybe for Vijay, another thing I was thinking is to have our GitHub open so we all can take a particular problem from DSA, start coding, and then once we arrive at a solution, and then we can talk about it, right? Each problem as we go, iterate half an hour, right? Every other day, whatever, right? Take time.
Correct.
Rather than going to basics and stuff. As we go through this, we'll invariably touch on basics anyways. That's how I'm thinking at this point in my head.
Yeah, and I was thinking about this too. Some of this stuff may be boring in the first month because people kind of already know a lot of this, at least this group does. But I think it would still be good to review it and just start with the basic lead code and really just practice that. And I think we can support, GitHub, put that as like part of
Yeah,
this.
I completely agree with Karthik. Maybe we should just spend 1 week of what do you say, kind of revising whatever is the concept, and we should get started with the problems, because invariably we will end up in digging deeper into each of these concepts. Because a theory, right, you will always think, I mean, you'll always feel that okay, you've understood, but only when you start solving the problems, you'll get to understand how much you have really understood, kind.
True,
So
true.
but just to kind of, what do you say, of course we will definitely need to, sometimes things will not be there on top of our mind, so maybe 1 week should be sufficient for us to touch upon all of these topics. I strongly believe all of us would have gone through this at least once previously, either in their either for any kind of interview preparation, for that matter. So,
Right. I mean, I've
So
gone
of
through all
all
of
this group, right,
Yeah.
I'll probably be the worst in this. I am not a computer science guy. I lived in this for a long time. Many times I wouldn't even know what is a heap, and I would be using it because I have used data structures for a while. So I'm the one who's going to be the least in the basics, but I'll try to catch up on that for sure.
Yeah, and I think like for that, right, here's the deal, right? Like, so for me, meeting up isn't so much, hey, we're gonna read a book and then we're gonna like talk about like all of this in great detail. It's not like the way we do it with this version of the study group for system design. This one is more like you're doing all that on your own, but what we are doing is we're going over so the first week will probably be like just a little bit of review, but then what I really do expect is like we're going to have more just sessions where we're trying to implement stuff together. So I almost envision like breakout rooms or maybe working together on the same stuff. Maybe like the first stuff could be like implementing one of these data structures from scratch. So if I say, hey, Karthik, and the rest of us, let's work on implementing, our first GitHub of a linked list, right? Or a stack, and then it needs to support all of these methods. Then I'll have each person write one of those methods, and then we'll just kind of like take a look at that. Maybe some of it could be done, even like on your own, but then we just kind of review it. And then we just kind of like talk about like things like, what is it good for? Like, and then the ON, time complexity, the ON space complexity. And then we also do the same thing, like after we are good with implementing a data structure, then we take a problem and then we also just, again, try this whole breakout room and we try to do it together. And then, yeah, like we just review. So it's just really like the main part of the group is just reviewing, right? Just, hey, review and practice. And that's it. And the rest is just your own time. Is that pretty good? It could be anywhere from 30 minutes to an hour. I'm even fine with making it smaller. If we want to have like one dedicated day to just do like the interview questions. So point in case is like, I have a friend right now that I'm working with, and every Friday, right, we just like do an hour where we set aside time to pretend like we're interviewing for another company. And so that person will ask me a whole bunch of questions. Mainly those are like JavaScript and React questions, but it could be like anything. It's like simulating like, okay, so tell me, what, the difference between state and props are in React, or, like, why do we need indexes as keys, right? So things like that. And so like, you kind of have to remember, oh yeah, did I study that? It keeps it top of mind. So I think having the same kind of like, interview practice with this group, like, oh, what's this? Can you implement it from scratch? That would be very advantageous because it keeps it top of mind. And then like going back and reading this kind of stuff makes it like really easy to like remember, oh yeah, okay. In-memory cache supports things like, like red-black trees, or, it's better for this or whatever, B tree, right? So just stuff like that. I want to keep all this like sort of like easier for me to remember in my head because there's so many things going on, if that makes sense.
Right. When are we getting started with this?
As soon as you want. But like I put May 15th because that's what Karthik said to me specifically. And then the other part of this is like, I want to keep it kind of small. I don't want to keep it huge because then like I think we'll fail. Like if we're reliant on too many people to like show up. I'd rather just kind of keep it small and pilot it and see how we go. So it's not for the faint of heart. It's only for people who really are dedicated or who want that
Absolutely.
accountability.
I mean, now also the design also, there are only few people who are, so that's okay. Let's get started from Sunday. Yeah, Sunday, Monday.
Sounds good. Okay, so I'll go ahead and create like a web page for this, and then like I'll just push this up if people want to see it, and then yeah, we'll get started with it, and then just basically just kind of go through. The other thing too I was thinking is that I will record some of the sessions and put them up to YouTube. That way, if people want to like follow along, they can passively. All right, well, good discussion. I got to get to another meeting by 9 o'clock. So thanks all for hanging out this long, and I'll see you next week. I'll let you know about the times for this when we start.
Yeah, sure. Thank you.
Okay.
Bye.
All right.
Bye,
Thank you all.
Vijay.
Bye.
Bye.